some here, but I don't see any.
Yeah.
It's just instructions. This one is locked. Sometimes it's in here. These are just worthless.
Yeah.
But the paper is the one that you
Through there.
Do you know who's supposed to provide that?
The instructors department is supposed to.
Oh, okay. Well, I guess I'll bring some paper next time.
Okay.
That's fine. There's usually just some here. I thought that.
Yeah, I think that's
That
just
would be the
things
case.
that other instructors have left.
Okay, well, I'll do that. I'll bring a box of paper. That's fine. I have something to write on right now.
You have enough for today?
Yeah, I have just this other paper. I'll just use that since it's fine.
Okay.
Good enough. Okay.
Hello, in the front. Raise your hand if you can hear this.
All right, so let's get started, I guess. All right, so in case there's any doubt, this is statistical signal processing. Let's go over some minor details about the class. Let's see. I haven't set office hours yet, but I think since the number of people in the class is fairly small, we can just do those by appointment. So when you need to see me, you just come and it's not working very well. You can come and see me. The books for the class, there's two of them actually. They look very much the same. These two things, Fundamentals of Statistical Signal Processing by Stephen Kay. We'll be covering about half of each one of these books. I realize that books are expensive, and so it's difficult to buy both of them. One thing you might want to consider doing is instead of purchasing the books, there's also the possibility of renting the books. There's a company called bookrenter.com. You can rent the books for a quarter for about, I don't know, a fraction of the price of actually buying. Okay, as far as grading and whatnot is concerned, so this is a traditional class in the sense that we're going to have homework, midterm, and a final. The final is a big chunk of the grade. Do you think you can shut off the sound from Silicon Valley? There's nobody there anyway. Okay, so here's a few other pieces of information. The midterm exam is tentatively for Tuesday, February 8th. The only reason it's tentative is because as the date approaches, we may be a little bit behind or a little bit ahead of the teaching schedule, so I might adjust the date a couple of days back or a couple of days forward, but probably it'll be the same day. And then, of course, the final exam on March 17th in class. As far as the rest of things are concerned, there's weekly homeworks. There's 8 of them. The last one won't be due. It'll be just a practice final exam. So the first homework is assigned today. It's already on the web page, and it is due on Tuesday, January the 11th, which is next week. The lecture notes are available here. This is basically more or less the things that I write down here, or some version of them will be scanned and placed online. The course is also being recorded, so the videos, I'll have a link here. I'll put a link once it's available to the course webpage. You can also visit the link and listen and watch the lectures again if you want to do that. Let's see what else. This syllabus down here is very rough, so we probably won't stick to this exactly, but more or less, it's a reasonable approximation of the things that we will do in the class. One last thing is that if you have already received a permission code, then you're all set. If you don't have a permission code and you need one, I have them here, so just see me after class, and I can provide you with a permission code. Let's see what else. Oh, and the Thursday lecture, so this week, Thursday lecture, I won't be here, but there will be a substitute lecturer, so please come. The material is not going to be any new material. It's going to be a review of a lot of probability and statistics and linear algebra, which we will heavily use in this class. So don't skip it just because I'm not here. Please make sure you attend. Okay, any questions before we get started about the logistics of the class? Okay, this is a small class, so we will adjust the speed at which I cover the material to slow down or speed up according to the level of interest that you have on the material. Don't hesitate to interrupt me at any point. I'm happy to answer any questions in the middle of the lecture and spend as much time as we need to make sure that the material is clear to everyone. So aside from that, I guess we'll go ahead and get started. Okay, so what is the point of this class? All of you who are in this class are probably here for because you have some kind of interest, whether it's research interest or just general academic interest, in problems that have to do with data processing. And so that is really the basic subject of this course as well. So the point, generally speaking, is that what we're going to do in this class is to see what happens when we take a bunch of data, and these are, another way to think of this is these are observations, okay, and we put them through some box. Okay, for now we don't know what's in this box, and what we're going to do is get two things out of this. One is to make a decision. Okay, so for instance, it might be that we're going to observe, let's say, the temperature, and let's say I observe the temperature in some place and I don't tell you where I'm observing this temperature. Okay, and then I ask you, well, I want you to decide whether it's summer or winter. Okay, that's a decision. I give you a bunch of temperature information. I say, in this location, which you don't know, is it summer or winter? That's a perfectly reasonable decision to make. Okay. Another thing, another example of this might be, let's say you have you record the audio from a very busy room. Okay. Let's say there's 50 people in this room. It's a big cocktail party. Everybody's having a good time. A New Year's Eve party. And I record the audio. I put a microphone in the room and I record everybody at the same time. Okay? And so that's this data. And then your decision is, I want to know if Mr. Robert Jones is in the room or not. Okay? Now, the voice of Mr. Robert Jones probably shows up in that, but it's all mixed up with everybody else's voice. Right? So it's not trivial. It's not obvious how one would do that. So these are, fairly benign examples of this. There are much more important and sort of life and death decisions that are made based on data as well. One of them is if you have the misfortune of feeling ill, you go to the hospital and the doctor doesn't know what's wrong with you, and so he or she might send you to the radiology department and they take some x-rays, or they do an ultrasound, or they take an MRI. And so that is then the observation. Okay? And based on that, they need to decide if you have a heart condition, or if you have a liver disease, or if you're fine. Okay? So those are more sort of critical types of decisions that you might want to make. Okay, so this part of transforming the data into decisions, that's sort of the first part of the class, and that is what's covered in the first book, which is Statistical Signal Processing Detection Theory. And so the idea of detection is the same as decision. So you're trying to detect the presence or lack of presence of some signal. The signal might be disease, the signal might be whether a person is present in the room or not, etc., etc. Okay. The second thing, the second sort of broad class of things that you might want to study, which we will study in this class, are that you don't necessarily want a decision. What you want is the values of certain parameters. Okay, so what would be an example of that? Let's say, for instance, what you observe is a bunch of data which are, let's say, audio recordings of, I'll give you a little bit esoteric example. The audio recordings of the sound of an engine. Okay? It's a car. The car is on, and you're listening to the engine. Without opening the hood and looking inside, you want to decide whether this car has 6 cylinders or 4 cylinders. Okay? Now, the number of cylinders, therefore, is a parameter. Right? It could be 4, it could be 6, or it could even be 12. Okay? Now, you can also think of parameter estimation as a decision, right? If the number of parameters that you have is only 2, then deciding between 4 or 6 is also a decision, right? The difference between these two is really not that big. You may have multiple decisions, right? Let's say if the engine has 4, 6, or 12, now you have 3 different decisions you have to decide between, right? But the difference between these fundamentally is that the parameter space is generally not discrete. It's continuous, okay? So for instance, you might, as in terms of data, excuse me, you might observe, again, an audio signal. And the parameter here might be the settings on your recording device. Okay. The treble and bass and all that stuff. Okay, so these are continuously adjusted parameters. You don't know what those are if you just get the recording. Somebody walks through the door and hands you a recording. Okay. And so those parameters, the difference between these is that decisions are typically discrete things, 1 or 2 or 3 or 4 different options. Parameters here are generally continuous things, and you're trying to extract a single value which has some specific implication, whether it's for medical applications or engineering applications. And so this is the second part of the course that we will be covering, and that's the second book. Now, there are situations as well where you're making a decision in the presence of unknown parameters. So those become composite decision-making problems, and I'll get into those in just a second. So just thinking, so basically the whole object of this course is to design this box. Okay? How to transform data into decisions, or how to transform data into optimal estimates of certain parameters that you might be interested in. All right, so as I said, as with all of these types of things that I described, there's a sort of hierarchy of different types of problems that you can consider. So let's think of those. And these are in some sense the hierarchy in terms of the level of difficulty that you might encounter. So one of them might be to detect a known signal in the presence of noise. Okay, so just going back to an example of this, this might be the example that I gave you earlier. You have a room full of people, everybody is speaking, it's a nice cocktail party, and then you have one person you're interested in, Mr. Robert Jones, let's say, and you actually know what Mr. Robert Jones sounds like. Okay? So now you have this mishmash of all the voices in the room that you've recorded with one microphone, and you're looking for this one guy. All right. Now, it's also possible that you know something about Mr. Robert Jones, but you don't know exactly what he sounds like. You have a really bad recording of him 10 years ago. Maybe he sounds a little different now. Okay? So you don't always have an exactly known signal. Sometimes the signal is not exactly known. In fact, it may not be known at all. Okay? So then you have both of these. You have an estimation to do, and you have a decision to make simultaneously. So that's a more complicated version of the same problem. So let me give you an example of a signal detection problem where the known is the signal is known. So as an example, consider these data points. So these are measurements. Let's say these are some constant plus noise. So this is a constant, and this is noise. Okay, so this could be just some constant value you're trying to measure. So all that's happening is that you're measuring some quantity, which if there was no noise would be just constant. Always you would measure always exactly the same thing, except that what you're measuring now is sort of fluctuating because of the effects of randomness or uncertainty. Okay, so the idea here is that for the case that I just described to you, this A is known. Now, generally, because you don't know if this A is there or not, you remember you're talking about a decision problem now, you have two hypotheses. What's a hypothesis? A hypothesis is a possible state of nature, right? You're kind of guessing that this might be true or this other thing might be true. So you have two hypotheses. We call H0 the null hypothesis, and this typically means the signal is absent. I'll describe this in more detail in a moment. And hypothesis 1, this means signal is present. Okay? Now, in terms of what this means in terms of this measurement equation, under H0, if the signal is absent, it means A is not there. Okay, so our measurements would be yn equals just noise. We'd be just measuring noise. And if the hypothesis 1 is true, it means that the data is A plus Wn. Okay? So the challenging thing about this problem is actually the fact that you don't know which of these situations you have. Right? Even if I tell you that A is some constant that is known, what you don't know, what you're trying to decide, is which one of these hypotheses does the data come from. Okay? And the idea is that you're going to collect all of these measurements, and basically you're going to stick all of these measurements y of n into this box and somehow come up with a decision that this signal, which in this case happened to be very simple, it happened to be a constant value A, if it's present or if it's absent. Okay? I might also ask you to tell me, I might also tell you, well, I don't know exactly what A is. I want you to estimate A. That would be a parameter estimation problem. I might ask you a composite version of this. I might say, I want you to tell me if a constant signal is present, but I don't know what its value is. So now you have a parameter estimation problem and a decision problem simultaneously. And that's sort of the most complicated scenario, which we come to at the sort of in the third part of the class, right? So the first part we're going to do decision problems. Second part we're going to do parameter estimation problems. The third part we're going to do decision problems where underlying parameters are not known. Okay, so and just to clarify, when I write this general form of y of n, what I generally mean is that this n is a bunch of measurements, let's say 1, 2, through capital N. So I have capital N data points. And so what I'm going to do is I'm going to feed all of these data points, y of n, where n equals 1 to capital N, into this box. And I'm going to come up with a decision. And the decision is you choose the null hypothesis or H1. Okay? So how do we design this box is the question that we will be addressing in this class. Oops. All right, so now let's go to, so what I'm doing now is just setting up the problem. I'm not going to solve it because these are going to be sort of the major milestones in this class in terms of the kinds of things we'll be doing. So let me go to the next step of this hierarchy, which I already mentioned, and this is the problem of detecting a known signal with unknown parameters. So let's say I have two hypotheses again, H0 and H1. Here signal is absent, here signal is present. When the signal is absent, I just measure noise. Okay? And when the signal is present, let's say I measure something much more complicated. I measure some constant A times sine of the following. N minus tau plus theta plus noise. Okay? So this is a sinusoid. This is an oscillating function. What I don't know is, I don't know A. Let's say I don't know the frequency. I don't know the time delay. I don't know the phase delay. Okay? But I know that the signal is oscillatory. I know that it has this form, but this is unknown, maybe this is unknown, and that's unknown. Okay? So that's one slightly more complicated version of the problem I just showed you. Okay? Even more complicated, or more general, one might say, is detecting random signals in noise. What does that mean? Well, here it would be y of n is equal to noise, and in the alternate scenario, y of n would be, let's say, some signal. Let me call it something very simple. Let's say s plus wn. Okay. Now the thing is, here, the s that I'm showing you, before I wrote it as an a, which was a constant, but suppose s here now is actually random. S is distributed according to some probability density function, p of s. Okay. And maybe I know the probability density of s, but I don't know the exact value of s. Okay? So s changes randomly. I don't know its exact value, but I know something kind of aggregate about how it changes. This seems like a nearly impossible thing to do. Yeah?
Is it just the value of S has a certain PDF, or is this the power spectral density of S?
Well, in this case, what I've done is I've just written a constant s.
Okay.
So in this case, the constant is going to have some probability density function. If this was something even more complicated, in other words, if this s was in fact changing over time, so if it was like this, then each value of s would have a probability density function possibly. And then the way you would characterize this is using the power spectral density. We'll get to that in the next couple of lectures. Okay? So the basic idea I'm trying to establish is the simplest case, and when you're trying to detect a known signal, I tell you everything about the signal. The next level is I tell you something about the signal. I tell you it has some form like this, but I don't know the parameters. And the next level of difficulty is where I tell you the signal, the only thing I know about it is some probability density, which is less than knowing an exact form for the signal. Okay? All right, so as I said, when you don't know the parameters, then this other scenario where you have to estimate parameters comes in. Okay? So let me just sort of summarize what I said. So this is 2. So the set of problems that I just described are a simple binary hypothesis test, which is you want to decide between H0 and H1, where everything is known about the signal. Okay, so that's one. So two, this is, again, the binary hypothesis test with unknown parameters. This is called a composite hypothesis test. It's composite because it involves both estimation and a decision. Okay? And then third one is the random signal case, which we'll come to later on. Okay? So this is all I described so far. This is, I didn't mean for this to be a very technical discussion. Basically, the last, whatever, 15, 20 minutes was a summary of the entire quarter. Okay? We're going to solve these three problems over the case of the over the course of the quarter. Okay? Now, each one of these can be generalized in many, many different ways. For instance, here we talked about a simple binary hypothesis test. In other words, you only had two hypotheses. What if you have three? What if you have n? Right? What if you have some large number of hypotheses? It's just a generalization of the things that you will learn in this class. Okay? So we'll talk about those kind of towards the end of the class. In this case as well, you have a simple hypothesis test with unknown parameters. What if those parameters themselves were not constant? What if those parameters were randomly changing? Okay? So like I showed you in this example, let's say here, right, I said what A, omega, tau, and theta were not known, right? But maybe A is also itself changing in a random way, and you know a probability density for it. Well, that's a combination of things that you're going to learn. Okay? All right, so this is a summary of the material that we're going to cover, and what I would like to do next for the more or less the remainder of this this lecture, and also for the next lecture, is to go over a review of probability and statistics and linear algebra. Once I'm done with this review, first of all, I'm going to assume that most of you, if not all of you actually, are familiar with most of these concepts. So if I'm writing things that you have never seen before, then I would make sure to go back and study these things and review them. And once I've said these, once I've gone through this review, I'm not going to go through it again. Okay, so I'm going to assume that everybody is going to be comfortable and completely fluid with these concepts, because these things are going to be used in a very, very regular basis over the course of the quarter. Okay, so let's do a review. And as I said, please, if you have questions, don't hesitate to interrupt me. Review of probability and statistics. Okay, so first of all, there's the definition of a probability space. We call this some big set omega, and this is the set of all possible events. Okay, and so there's two things. Then there's a function probability, which assigns a scalar likelihood, which is what we call a probability, to each of omega. So for example, if your probability space, if the set of experiments that you're looking at are which side of a coin lands when you flip it, then the probability space, the set of all possible events, you get heads or tails. Okay, we're going to assume the coin is not going to land like this. Okay? And probability assigns a scalar likelihood to each element of omega. Okay, so if you get heads or tails, if a fair coin is tossed, then you get 1/2 and 1/2. Okay? That's a very, very simple example. Now, then you have events. Event A is something that is that lives inside this omega, and the probability of an event is always a number between 0 and 1. So for example, the probability of heads landing or tails landing, this is the experiment, okay, flipping a coin, and this is the probability which lands between 0 and 1. Now, given this expression, what is the probability of the entire set? Well, that has to be 1. Right? What does this mean? Probability of omega means the probability that any of the events happen from the set. So what this really means is probability you'll get heads or tails. And so of course that has to be 1. So when you flip the coin, one of them has to land. Okay. Now, what if you have multiple events? So let's say if you have 2 events, say A and B, okay? And these events, so you might have a set like this, which is the set of all, the entire probability space, the set of all possible events, and then you might have 2 events, A and B, and these events might in fact intersect with each other. They might have something in common. Now, in the case of the coin flip, they don't have anything in common, right? When you flip, you either get a head or you get a tail. But that's not always the case. Sometimes there's an overlap between the set of possible outcomes of an experiment. So if an experiment was, for instance, instead of flipping a coin, you flip 2 coins at the same time, right? It's possible that these 2 coins might both be heads, one might be head, one might be tails, the other way around, or they both might be tails, right? So if now you do 2 experiments, right? And you look at the outcomes, it's possible that those outcomes will have 1 head or 1 tail in common. Okay, so there's some overlap is possible. Okay, so now if you have an overlap between events, then sometimes you're interested in finding out things like what is the probability of an event A or B happening. Okay, this is also, it's possible to write this as A union B. Okay, so in terms of that picture that I showed you, A union B is the set of all points that is covered by both of those sets. Okay, so the general expression for this is that this is equal to probability of A plus probability of B minus the probability of A intersection with B. Okay, now why do we have to take this out? Let me show you this picture again. Okay, if you look at this picture, probability of A union B. A union B is the set of all the points that are covered by A and B, right? Now if you look at this, if I do probability of A plus probability of B, I'm counting this area here twice. Okay, so I have to take that out in order to make sure that I get the correct answer. And furthermore, this term here, A intersect B, this would be 0 if A and B are mutually exclusive. In other words, if A and B have nothing to do with each other, then probability of A or B is simply the sum of the probabilities of A and B. There's no intersection, there's nothing to subtract. Okay? All right, so this was for OR. What about the probability of A and B? Okay, so now we're talking about the area of intersection between those two sets that I just wrote down. So this is the probability of A intersect B. Okay? Now this happens to be equal to the probability of A times the probability of B if and only if A and B are independent. So if these are independent events, then the probability of their intersection is just a product. So what is an example of two independent events? Two independent coin tosses. Okay. So if you toss a coin twice, and you get, and I'm going to ask you, what is the probability of getting heads and then tails? Okay. Then if the two coin tosses don't have anything to do with each other, then it's just the product of the two. Okay. All right, now with these two in place, the next very important concept is that of conditional probability. So, conditional. The idea of conditional probability is to look at what is the probability of A given B. Okay? So here, we have two events that obviously have something to do with each other, presumably, and we're asking what is the probability of observing the event A given that the event B has occurred. Technically, the way to write this is the probability of A given B. Okay. Now, what this equals is the probability of A intersection with B normalized by the probability of B. Okay. Now, if you think about this again in terms of this picture, what is it asking? It says, I want to know what is the probability that this event A has occurred, given that I know B has occurred. Okay. So obviously, this probability is not this entire thing, but it is confined to the area of intersection between A and B. Okay, because you're saying it's given B. Okay, so it's confined to this area. But it also has to be normalized. It has to be normalized because you know that the B has already occurred. So it's basically this area normalized by the probability of B. You can also write this in the reverse direction. And that would be the probability of B given A. And this would be the probability of A given B. This time normalized by the probability of A. Okay? So let me rewrite what I had in the previous page. Probability of A given B is the probability of A intersect B divided by the probability of B. Okay? So what you see here is that the only thing that's different, when you reverse the order of the conditioning, the only thing that's different is that normalization factor in the denominator. Okay? The intersection part here is exactly the same. Now, if we take these two expressions and consider them at the same time, what you can see is that this term can be written two different ways. Namely, I can write probability of A intersect B as the product of B given A times A, or I can write it as probability of A given B times B. Okay? So from these two, I can derive that the probability of B given A times probability of A is probability of A given B times probability of B. Okay? And what this shows me is a way to reverse the conditioning of the probability. So if I have, let's say, probability of A given B, and I want probability of B given A, this tells me a way to do it. So for instance, probability of A given B is therefore equal to probability of B given A times probability of A divided by the probability of B. Okay? This is just rewriting this last expression to this line. Okay? This is an important property to be able to use later on, because sometimes you're given an event A and sometimes you're given an event B, and you want to find the conditional probability in the reverse direction. So let's see what are some of the consequences of these types of conditional probabilities. So suppose I think of the situation where A and B are independent. So suppose A and B are independent. Then what that means is the probability of A intersection B is just the probability of A times the probability of B. Right? We saw this in the previous page. Right? If and only if A and B are independent, this intersection is just the product of the two probabilities. So what does this mean? It means that if I now take this and I consider this, let's say in this expression here, what do I get? I get the probability of A conditioned on B is, the numerator is this guy, but I'm going to replace it with this. So I write probability of A times the probability of B, and then I divide by probability of B. And what do I get? Just probability of A. Okay, so what this means is that if A and B are independent, then the conditional probability gives me exactly the same as the unconditioned probability. Why? Because B is not giving me any information about A. Okay? And the same is true, of course, if you do this for B given A. If A and B are independent, probability of B given A is just probability of B. Okay? So you don't need to deal with the conditioning if the two things are in fact independent of each other. All right, so everything that I spoke to you about so far was about sort of discrete events, A, B, and so on. The next step to take all of this is to talk about random variables. Next. Okay, so what's a random variable? Let's take the random variable to be, let's say some x. Okay, so a random variable x is a quantity that can take on different values with different likelihoods. Okay, so basically an event can be a particular value of the random variable being selected. So we choose this x not to specify a specific number necessarily, but to specify a collection of possibilities which occur with different likelihoods. So how do we specify these likelihoods? We do it using what's called the probability density function. And that's Px. And we think of this for now as a continuous random variable. Discrete versions of it we can talk about as well. The description is very, very similar. Okay, so we think of this as the probability density function P of x. And what P of x does is the following. Let's draw this axis here. Let's call this x. This is the real axis for the case of a single random variable. And the values, all the possible values of x occur along this axis. Okay, so it might be from, let's say, minus infinity to infinity. Then this P of x is a curve, and it might have some shape, I don't know what, let's say it's like that. And now I take a particular value x here, and I want to ask what is the probability that x falls between, let's say, x0 and x1. Okay? Now this is an event. Okay? The particular value of x falling between these two limits is an event, and I can compute its probability. So let's say x0 is some little difference between x and its neighbor. Okay? Then, if I look at this area underneath this curve, this is P of x. If I look at this area, this is, in fact, this probability. Okay? So that's why this is called the probability density function, because it allows you to compute the probability of an event, which is x occurring within some region. Now here's a slightly tricky thing about all of this. What if I wanted the probability that x is exactly equal to some number? What is it? It's 0. Because the area under a line is actually 0. Okay? So we never really talk about a continuous random variable having a probability of occurring and giving you an exact answer. We always talk about the probability of a random variable being in a small neighborhood of a particular number. Because if we shrunk that neighborhood to a specific value, the probability would be exactly 0 in the continuous case. Okay? So this is something slightly delicate that one has to be careful about. Now, we can do this in a, like I said, in a small neighborhood. So let's suppose, as I said, let's say x1 is equal to x0 plus dx. And this dx is sort of the differential that you're familiar with from calculus, right? So now what you have is you want to find out what is the probability of x being between x0 and x0 plus dx. Okay? So now what I'm asking you to do is to shrink this area under the curve to a really tiny rectangle underneath. Okay, so that would be something that maybe would look like that. Okay? Now in this tiny rectangle, this value can be used to approximate the area of that rectangle. Okay? So this would be probability, would be the value of PDF at x0 times dx. Okay? So when the area, when the region that you're looking at is differentially small, then you can just multiply the value of x0, the PDF at x0, times that dx to get an approximation, a very good approximation to the value of the probability you're looking for. And we can use this later on to define the the cumulative distribution function as well. So what are some of the properties of this PDF? Properties of this P of x. Well, a couple of very important ones. The first one is that if you integrate, let's say this x here is going from minus infinity to infinity. If you integrate px dx from minus infinity to infinity, you have to get 1. Okay. Why? Because if I now take this expression here, okay, and I integrate this expression on both sides, what you see is that on the left side, I will be summing up the probability that x is between x0 and x0 plus dx, and summing it up with all the other probabilities across the entire range of definition of x. So my left-hand side would have to be 1, and therefore my right-hand side, once integrated, would also have to be 1. Okay. So this is exactly the same as what I showed you earlier, which was this expression. Okay? The probability of the entire set occurring is equal to 1. This is basically just another way of writing this expression here. Okay, the second property is that the PDF is always a positive function. Okay? Because you're talking about, if you just divide both sides of this by dx, okay, what you have here is that this right-hand side, this left-hand side is always positive. So you're talking about something that measures probability, so it would have to be positive. Okay. Now, the cumulative distribution function, or CDF. This CDF is basically the integral. So you remember we had the PDF, which is this little p of x. The CDF is, we denote this with a capital P of x. This is the integral from minus infinity to x of, let's say, p of tau d tau. Okay, so if the PDF, let's say, looks like this, let's say this is little p of x, then you go from minus infinity to some value x, and this area is the value of the capital P of x. Okay? So now if I take this x and I keep moving it to infinity, what am I going to get? As x goes to infinity, then this value has to be equal to 1, because I'm looking at the area under the entire curve. Right? So typically P of x has the following look to it. It starts at 0, because if you push this out to infinity, to the left, minus infinity, you get 0. So it starts at 0, and then it comes up, and then it settles down to 1. Okay? And it's an asymptote at 1, and this is 0. This is meant to be very smooth, but that's as well as I can draw it. Okay, so what this shows you is basically the probability density function and the cumulative distribution function are related to each other by an integral. You can also reverse this using just the fundamental calculus. What this means is the PDF can also be written as the derivative of the CDF. Okay, this is just the reverse of that expression, assuming that P at minus infinity is in fact equal to 0. Okay, so everything that I said here was for continuous random variables. For discrete random variables, the business is very simple and very similar. The difference here is that random variables that are discrete have only a finite number of values that they can take. So for instance, you might have a discrete random variable which can take only values x1, x2, x3, let's say xm. Okay? So x can take on these values. So for instance, instead of x going from minus infinity to infinity across the real numbers, suppose I restrict the range of x to go from minus 10 to 10 and take on only integer values. Okay, so you can have minus 10, minus 9, minus 8, all the way to 7, 8, 9, 10. Okay. There's only a finite number of values there. And each of these, therefore, is going to have its own likelihood of happening. Okay? And therefore, each of these is going to have its own probability associated with it, which we're going to call P1, P2, and so on. Say PM. And therefore, the way we describe these probabilities is that we draw a picture. So let's say we draw x here, and these are now going to be the discrete values, let's say x1, x2, x3, and so on up to xm. Okay? And each one of these is going to have some probability associated with it. So this is going to be P1, P2, Pm. Okay? And so the way these have to add up now is the sum of pk, k equals 1 to m, has to add up to 1. And of course these p's, the pk's are all positive. Right? So this is sort of the discrete equivalent of this integral these are just the discrete equivalents of these properties that I just showed you for continuous random variables. Okay? So in this case, you can still define a cumulative mass function if you want, but generally this is enough to give you all the information you need. So everything that we're going to talk about for continuous random variables can also be done for discrete random variables, but we will generally talk about continuous random variables from this point forward. Okay, so again, going back to continuous random variables, then we have the idea of moments of random variables. So the first one is the concept of the expected value, E of x, the integral of x times the PDF x dx. The notation for this, we sometimes use x bar, sometimes we use mu sub x, sometimes we use m. Whatever you want to call it, this is called the expected value. It generally refers to if the p of x has a shape that is symmetric, like this, typically E of x corresponds to the center of the bump. Okay? Now if it's not symmetric, then it's not going to correspond to that. So let's say if it's, suppose it looks like this. Okay? Then the expected value is probably going to be sitting somewhere over here. Okay, so you can't always go to the peak and expect that to be E of x. The idea of the expected value can also be more generally defined for any function of the random variable. So for instance, I can ask, what is the expected value of some f of x? F of x is just some function of x. X is a random variable. F of x could be x squared, it could be exponential of x, whatever. That's simply the integral of p of x times f of x dx. Okay. So the simple random variable was x. Here I just replace it with f of x. So for instance, the expected value of x squared, this is the integral of x squared px dx, and this we call the mean squared value of x. Don't confuse this with the variance. This is not the variance yet. Okay? The variance is something related to this. The variance of a random variable, which we denote by sigma squared, is the integral of x minus the mean squared times p of x dx. Now if you expand this out, you get the expected value of x squared minus the square of the mean. And this is the variance. Okay, so if the variance happens to be 0, I'm sorry, if the mean happens to be 0, then the mean squared value and the variance are the same. Okay? And just as a reminder, sigma without the square is also referred to as the standard deviation. Why is it called the standard deviation? Because if we have a random variable which has a PDF that's like this, kind of symmetric, so this is x, and let's say this is the mean, m, the standard deviation gives you an idea of how wide this bump is. Okay? So the basic rule of thumb is that this width, if you go 2 sigma to the left and to the right of the mean, you get 90% of the area under the curve covered. If you go 3 sigma, you get like 99% of the area covered. Okay? So if sigma is bigger, that means that this is going to look more like that. Well, it has to, the peak has to come down, so it has to look kind of like this. Okay? So the chubbier it gets, the wider it gets, the larger the sigma. Okay, all of this stuff, any questions? It's a fairly basic stuff so far, right? Okay, so some of the things that we will be using very often One of them is the Gaussian random variable. It's also called the normal random variable. The probability density function for that is 1 over square root of 2 pi sigma the exponential of minus 1/2 x minus m squared divided by sigma squared. Okay? So m is the mean, sigma squared is the variance. We also denote it as x with the tilde here, normal, mean, sigma squared. The shape of it is like what I showed you. This is the classic bell curve. Looks like this. The mean is here, and the sigma is going to give you the width of the random variable. Okay? Can you do me a favor and put your phone away? Thank you. All right, if you have two random variables, let's say A and B. The expected value of some linear combination of these, let's say alpha A plus beta B. This is simply alpha, expected value of A, plus beta, expected value of B. What about variance? Variance of alpha A plus beta B. This is going to be alpha squared, variance of A, plus beta squared, variance of B, plus 2 alpha beta times the covariance of A and B. Okay? Covariance is an indication of the dependence, of the linear dependence between two random variables A and B. So if A and B are not linearly related to each other, then this term would be 0. The covariance is defined like this. Covariance of A and B is equal to the expected value of A minus A bar times B minus B bar, where A bar and B bar are the mean of the respective random variables A and B. Okay? So it's like the variance, except that it's not the same variable inside here. It's A and B, and so that's why it's called the covariance. Don't worry if you're not catching the stuff before I move on to the next slide. It's all on the web. You don't really have to take the notes if you don't want to. Okay, so with two random variables, things get interesting. So let's think about. Suppose you have two random variables. Let's call it x1 and x2. Sometimes we will denote these as a vector. We'll write x with an underbar, and we'll say x1 and x2 like this. Okay. Now, when we have two random variables, now if we want to describe their probability density, we have to describe their probability density at the same time. Okay. So this is what we call the joint PDF between these two, and that's P of x1 and x2. We can also write this as P of x like this to denote that it is the joint probability density function between these two. Now, we can also, from the joint probability density function, extract the probability density function for each one of the random variables. So that would be P of x1 and P of x2. So suppose we wanted these and we were only given this. Well, the way to do this is to integrate out the variable that we're not interested in. So this would be the integral of P of x1, x2 times d x2. Okay, and correspondingly, this would be the P of x1, x2 times d x1. Okay. These are called marginals. Marginal PDFs, marginal probability density functions of the original PDF. Okay, now let's see how we describe the joint PDF. Well, if you remember from earlier, we talked about conditional densities, right? So let me take you back for a moment to one of these earlier slides. Yeah, so let's take a look at this. Okay? Probability of A and B is probability of B given A times probability of A, right? Now here, this is the PDF of x1 and x2. So kind of like that. Okay, except that this is a probability, this is a PDF. But it turns out the expressions will be very familiar in terms of the way the final result turns out. So the joint PDF can be written as the PDF of x1 conditioned on x2 times the PDF of x2. Okay, so this should be very familiar from that expression that I just showed you. And correspondingly, if you remember, we can write this in the reverse way, x2 given x1 times the PDF of x1. Okay. And so again, using the same trick that we did before, you just rewrite this. You get PDF of x1 given x2 is equal to PDF of x2 given x1 times the PDF of x1 divided by the PDF of x2. Okay. So if you're given a conditioning for one variable and you want the other one, this is the way to do it. And this is, of course, closely related to what's called Bayes' theorem, right? So if you want the conditioned densities in terms of the joint density, you can now take this numerator, okay? And that numerator, of course, is going to be this P of x1, x2, and you can put that in here. And now what that shows you is that you can take the conditioned density and write it in terms of the joint density, or the other way around. Okay? So it's a very useful trick to be able to use in terms of solving various types of problems. Okay, now when you have two random variables, we also think about the covariance between the two random variables, just as I described to you before. The covariance between x1 and x2, just to rewrite it, the expected value of x1 minus its mean times x2 minus its mean. Okay? Related to this is the so-called correlation coefficient. The correlation coefficient, we call that rho, is a normalized version of the covariance. This is the covariance of x1 and x2 divided by the square root of the variance of x1 times the variance of x2. Okay, so another way to do it is you can write covariance of x1, x2 divided by sigma 1 times sigma 2. Variance of x1 is like sigma 1 squared, and variance of x2 is like sigma 2 squared, so you take the square root, and this is what you get. Okay? Now, what is the meaning of the correlation coefficient? Okay. The correlation coefficient, rho, is a number between -1 and 1, always. Okay, and the reason why it's between -1 and 1 is because of this normalization factor. So what does it mean when rho is equal to 1, or when rho is equal to -1? What it means is the following. When rho is equal to 1, it means that you can write x2 as a times x1 plus b for some a and b, where a is strictly positive. Okay? In other words, it means that the two random variables are perfectly linearly correlated. Okay? People often make the mistake of thinking that somehow because rho is equal to 1, x1 and x2 are somehow more strongly related to each other than this. Okay, the reason I write this very explicitly is because I want to give you an idea that the dependence between x1 and x2 when rho is equal to 1 is only linear. Nothing more and nothing less. And in fact, if rho is equal to minus 1, then it's exactly the same thing except that the A has to be negative. Okay. All right, now let's generalize this to the covariance. Let's go back to this covariance idea and generalize it to the covariance of a vector, x. Okay, so now if I want to look at the covariance of x, this is the way we write this. It's the variance of x1, covariance of x1 and x2, covariance of x1 and x2, and the variance of x2. Okay. Now how does this work? Let me rewrite it in a slightly different way. Okay. We'll just put that up there. Remember, the expression for covariance is this, right? This for the scalar covariance. For the vector covariance, the expression is very similar. The covariance of x is the expected value of x minus its mean times x minus its mean transpose. Okay? X is a vector. So x times x transpose becomes a matrix. So this is the expected value of a matrix, which is basically this expression here. Okay, so if you expand everything out and simplify, this is what you will get. The covariance of x is this matrix quantity. So let's just remember the dimensions of these things. So this guy here, the way I wrote it, it's a 2 by 1 vector. And this here is a 1 by 2 vector. Right? So when you multiply them, you get a 2 by 2 matrix, which is exactly what you saw earlier. Okay. So the covariance, the way we had it for the 2 by 2 case, the covariance of x is sigma 1 squared, sigma 2 squared here, right? And then there's the covariance between x1 and x2 here, which turns out to be rho times sigma 1 sigma 2 and rho times sigma 1 sigma 2. This is the case for the 2 by 2 covariance matrix, where this rho is in fact the correlation, which is between minus 1. Okay. One other important thing to keep in mind is that the covariance matrix, actually regardless of the dimension of x, the covariance matrix is always a symmetric matrix. Okay, so if we call, let's say Cx, we call this the covariance of x. And x could be a long vector, not just 2 by 2. Then Cx transpose is equal to Cx. Okay. The reason why is because if you look at this expression here, covariance of x1, x2, I could have written this as covariance of x2 comma x1, but it makes no difference. It's exactly the same. So the off-diagonal terms are always equal, which is the definition of a symmetric matrix. Okay, just to kind of clarify things, so if rho is equal to 0 in this case, what do you get? You get that this Cx is equal to sigma 1 squared 0, 0, sigma 2 squared. Okay? This means that x1 and x2 are uncorrelated. Okay? Now, a very important concept is the difference between uncorrelated and independent. Those two things are not the same. And I want to make sure that we're all on the same page as to why that is. There are various examples that I will put on the course webpage that you can look at. So let's see, what does uncorrelated mean? Uncorrelated means the covariance of x1 and x2 is equal to 0. Right? That's the off-diagonal term that we just looked at. This simply means that the expected value of x1 minus x1 bar times x2 minus x2 bar is equal to 0. And if you just multiply these and simplify things out, what you get is that this means the expected value of x1 times x2 is the expected value of x1 times the expected value of x2. Okay, this is what uncorrelated means. Okay? On the other hand, independence means the PDF of x1 and x2 is equal to the PDF of x1 times the PDF of x2. Okay? This is independence. This is uncorrelated. Now ask yourself, of these two expressions, which one is stronger? The one that deals with the moments, or this one? The second one is a much stronger statement, right? Because the probability density contains in it information about all the moments, right? So when you say P of x1, x2 is equal to the product of these two things, this is a much stronger statement than saying it's uncorrelated. So it turns out that independence implies uncorrelatedness, but the reverse is not true. Okay? So here's the way it works. Independence and uncorrelatedness. Independence implies uncorrelatedness, but this is not true. Okay? Now there are some exceptions, and these are pretty important exceptions to this case, where in fact uncorrelatedness and independence are one and the same thing. And that exceptional case is the case of the Gaussian random variable. So if you have two random variables that are jointly Gaussian, then if they're uncorrelated, they're also independent. It's true also if you have n Gaussian random variables. And the last thing that I want to do is to take you over that and to show you how this all works before we finish for today. Okay, so before we do that, let me just generalize the idea of covariance to a matrix that has more elements than just two. Let me just write x is equal to, say, x1, x2, let's say we go to xn. Okay? And so when we do this, the expected value of x is also going to be, m1, m2, mn. And we denote this also as m bar like that. Okay? So now let's go to the covariance. Cx, this is the covariance, this is the expected value of x minus m times x minus m transpose. And what this is going to look like is a matrix, which is a big matrix, like this. Along the diagonals is going to be the variances, sigma 1 squared, sigma 2 squared, and so on, up to sigma n squared. And along the off diagonals, you're going to have the covariances between the various elements of x. So let's say we take some position here, let's say j, and some position here I. So if we go here, let me use a different color so you can kind of see better. So if we go here, I and j, this position, the value in that position would be the covariance of xi and xj. Okay? And so correspondingly, if you go to the jith position, that would be the covariance of xj and xi, which would have to be exactly the same. Okay? And so this matrix, this whole matrix, this is an n by n symmetric matrix. Okay. in the general case. Okay, so now with this in hand, let's talk about the Gaussian, which is the case where, as I've shown you, as I've indicated already, the multivariate Gaussian is the case where you get the independence and uncorrelatedness are basically one and the same thing. Okay, so now let's look at multivariate Gaussian. So let me write it in the next page. Okay, so the PDF looks like this. 1 over 2 pi to the n over 2 square root of the determinant of c times the exponential minus 1/2. Oh gosh, I'm running out of space. Okay, over here. X minus m transpose c inverse x minus m. Okay? Another way to denote this is we write x is a normal random variable with mean m and covariance c. And of course, if the covariance of xi and xj are equal to 0 for all I not equal to j, then C is going to be a diagonal matrix. It's going to look like this, sigma 1 squared to sigma n squared, and all zeros over here. Okay? All right, so now let's suppose that this is true. So let's suppose that C is in fact a diagonal matrix, sigma 1 squared, sigma 2 squared, sigma n squared. Okay? All right, now what I want to do is to look at this exponential term. Let's look at the exponential minus 1/2 x minus m transpose c inverse x minus m. Okay? All right, so let's look at this this bit in the middle. So you have minus 1/2. What's x minus m? It's x1 minus m1 to xn minus mn, like this. And then there's a diagonal, sigma 1 squared, sigma n squared. And then the matrix, the vector x1 minus m1, so on, xn minus m. Okay? Everybody agree with this? All right. So now I'm just going to multiply these out.
That should be the inverse of C.
Yes, I have to put a minus, well, I can put minus here, like that.
Why do you need to multiply them out?
I'm sorry?
Why do you need to multiply them out?
Well, what I would like to do is to eventually show you that this probability density function, when C is a diagonal, is equal to the product of the PDFs for each of the individual elements of X. And therefore demonstrate that for the Gaussian, independence and uncorrelatedness are the same. So this, I guess you were outside the room when I described this just a minute ago. So the way to do that is to show that the PDF for the joint PDF for X is the product of all the PDFs for the individual components of this. So if we multiply this, this will show up fairly easily. So let's multiply, and what we get is the following. You get this exponential minus 1/2 times, well, let's take a look at this. So let's look at what the first term, first of all, this is going to be a scalar, right? This is a 1 by n by n, and n by 1. So this whole thing, once I multiply it, is going to be a scalar. The scalar is going to be a sum of a bunch of terms. The first term is going to be x1 minus n1 times sigma 1 to the minus 2 times x1 minus n1. And every term is going to look exactly the same as that, okay? Just with different indices. So this is going to be minus 1/2 x1 minus m1 squared divided by sigma 1 squared. That's the first term, okay? And all the other terms are going to be the same. Minus 1/2 x2 minus m2 squared divided by sigma 2 squared, and so on, plus minus 1/2 x1 xn minus mn squared divided by sigma n squared. Okay, so this is the exponential of the sum of a bunch of terms, right? The exponential of a sum can be written as a product of a bunch of exponentials. So this is equal to the exponential of minus 1/2 x1 minus m1 squared divided by sigma 1 squared times a bunch of terms up to minus 1/2 xn minus mn squared divided by sigma n squared. Okay? Now, there's going to be this normalizing coefficient in front as well, but that normalizing coefficient is also going to be a product of a bunch of terms, because the determinant of C is just going to be the product of these variances. So those individual variances can be separated into pieces, shared with each one of these exponentials, and the net result is that this whole thing is going to yield the PDF of x is going to be the PDF of x1 times the PDF of x2 times the PDF of xn. Okay? And this means independence. Okay? So uncorrelated implied independence if and only if x is jointly Gaussian. Okay, this is really important. So what I said here was independence implies uncorrelatedness, but uncorrelatedness does not imply independence. But here I'm saying uncorrelatedness does imply independence only if it's Gaussian. So the Gaussian is an exception to this reverse arrow not holding. Okay. There are a few other cases, but they're kind of esoteric and you don't need to worry about those. Just remember that independence is a stronger concept than uncorrelatedness, therefore it implies uncorrelatedness, unless you're talking about a Gaussian, in which case the two concepts are one and the same. Okay. Okay. Any questions? Yeah.
Every covariance matrix should be positive definite. Yes?
I'm sorry, say that again?
Every covariance matrix
Covariance
should be positive definite.
That's right. Every covariance matrix is also positive definite. So we'll get to that in the next couple of lectures. We'll talk about what positive definiteness means and so on.
And the inverse is also true.
What's the inverse?
I mean that if we have a matrix which is positive definite, can we find random variables?
You can always define a random variable that has that as its covariance. Yes, you can define one. Right. Okay, so generally we'll stop at 11:30, which is what we're doing in the next few minutes. We typically do administrative stuff for the course, or if people have questions and so on. But if you don't have any questions, then you're dismissed for this time. And remember, the next lecture we'll have a substitute lecture. It'll be a continuation of review material mostly. And most of next time we'll talk about some statistical concepts and also linear algebra, which is a very important part of this class. So this kind of starts with the positive definiteness and what that means, and singular value decompositions and eigendecompositions and so on and so forth. And then towards the end of that lecture, and most likely next week, we'll start really solving simple detection problems and actually defining what the solution to these things means. Okay, so no questions? Okay, if you need a permission code, just come see me. Otherwise, I'll see you next week. Yeah.
Yeah, I need a permission code.
So you're a grad student?
Yeah.
Okay. Hold on 1 second. Which department are you in?
I'm one of 10 students.
sorry?
I'm one of 10 students.
Okay, right.
Yeah.
Six, seven, six. Zero, one, five. Okay? If that doesn't work, just email me, I'll give you another one. It should work.
Yes. So is most of the class matrix related signal processing?
You have some background in signal processing?
A little bit.
Okay. You need permission to? Okay. All right, so yours is this one, 108-005. 005. Okay. And which department are you in? EE.
I'm going to log out and so I'll run the
Yeah, I'm all set.
Well, it was either 240 or...
So there's no class following this one?
I don't know.
Oh,
I'm gonna log out and then.
I guess I can log back in, I guess. All right. All right. Okay, have a good one.
You too.